NASA's James Webb Space Telescope has documented a celestial object from the early universe that operates outside the known laws of physics. This source emits 100 billion times more energy than our Sun, but its light signature shows no evidence of the nuclear fusion that defines every other star we've discovered. MIT researchers have identified this as a black hole star, a classification of matter that had until now existed only in theoretical models. When an object displays properties that should be physically incompatible, it forces researchers to re-examine how the first structures in the cosmos were built. This discovery addresses a puzzle that has shadowed the James Webb mission since 2022, the observation of hundreds of little red dots appearing across the deep past. These sources resemble small, distant galaxies, yet their energy output is too concentrated for any standard collection of stars. To find an answer, Rohan Naidu and his MIT team isolated a target from just 660 million years after the Big Bang. They focused on MOM BH star 1, the reddest and most luminous anomaly identified in the survey. The data revealed a chemical footprint identical to a star, yet the object was radiating with the raw power typically seen in black holes. Analyzing the physical mechanics of this object provides a framework to identify thousands of similar red sources scattered throughout the telescope's archives. When astronomers see extreme red hues in deep space, the standard conclusion is that the light is passing through dense clouds of interstellar dust. This chart shows that the light from MOM BH star 1 is essentially unaffected by dust. The red color is coming from a different physical process entirely. The team identified a sharp drop-off in the data known as a Balmer break. This occurs when light waves are absorbed by a wall of hydrogen gas so thick it behaves like a solid screen. With dust ruled out and a massive hydrogen barrier confirmed, the team used computer simulations to find a physics engine that could actually produce these results. The structure of a black hole star differs from stellar arrangements in our local neighborhood. At its center sits a forming black hole with the mass of 100,000 suns. Surrounding this core is a massive cocoon of hydrogen gas, forming a shell that spans the size of our entire solar system. Instead of nuclear fusion, this system is powered by accretion. The central black hole is violently consuming the surrounding gas envelope. This feeding process releases massive amounts of radiation. As that energy pushes through the dense hydrogen shell, the gas scatters the light, causing the entire system to glow red. This configuration allows a single black hole to masquerade as a star, radiating immense energy while remaining hidden inside its own gas supply. The existence of MOM BH star 1 confirms that many of the little red dots spotted by the Webb telescope are likely black holes caught in this specific stage of growth. This challenges the traditional view that black holes must form through the explosive death of a star. Black hole stars represent a non-explosive, direct collapse pathway that is far more efficient than supernova-based formation. By bypassing the slow evolution of a standard star, these objects were able to reach masses of billions of suns while the universe was still in its infancy. This growth phase acts as a bridge between small, early black holes and the supermassive giants found in the centers of modern galaxies. These objects served as the primary gravitational centers that governed how the very first primitive galaxies took shape. By drawing in massive amounts of gas, these early anchors created the gravitational stability required for subsequent generations of stars and planets to coalesce. By identifying this red mirage, astronomers are finally mapping the specific stages of growth that led to the formation of the Milky Way and our own place in the cosmos.